There we go. So on Thursday, I will help you with the tutorial homework, tutorial number 3, and hopefully show you that those problems are really very much the same as examples 4 and 5 in chapter 17 of your book. And so hopefully that will kind of make those homework problems in the tutorial seem pretty doable. And then on Thursday, I'm just going to work problem after problem after problem, the types of problems you can expect on the exam to help get you feeling comfortable with that. As you are aware, there are 2 sample exams at Max, as well as their solutions. And again, I exhort you, like I did in 105, whatever you do, don't look at that key. Don't look at the solutions until after you've pretended that that sample exam is real. You're just going to fool yourself if you just read through the key and say, oh, wasn't Greg clever there? Yeah, I see what he did. That's not going to help you when you're on your onesies in the testing center. Okay, so you've got to actually pretend that it's real and then grade yourself afterwards. Okay, and if you find that you just have no idea how the solution key got that answer when you got this answer, then you need to talk to someone. You need to either go to the help center or come to me, need to figure it out before you go and take that exam. Now, the tutorial homework is not due until Monday night at midnight, but I would encourage you to do that homework before you go to the testing center to take the exam. And I don't want all of you going to take the exam on Tuesday. That just seems cruel for the people over at the exam testing center. Thursday night at 7 o'clock, I will be in this room answering questions that you might have. I will record that review session and post it at YouTube, and you'll have access to that if you can't come in person. Are there questions before we get started on today's lecture? Yes, sir.
Is there a place on Max we can find what the equation sheet will look like that we'll have in the testing center?
The equation sheet is exactly the same as the equation sheet on the sample exams. I actually took a screenshot of that equation sheet and put it on the front page of your exam. Okay. Okay. Let me go back here. Today we're going to kind of take advantage of the fact that many of you enjoy the outdoors, and many of you have been out hiking in the wilderness, and I hope some of you learned how to use a topographical map. And you can look at this map and you can just visualize where the mountain peaks are. You can visualize where the cliffs are, where you want to avoid hiking in the dark. Okay, these lines on a topographical map represent everything on a line represents the same elevation. And so if I have a lot of these lines that are close together right there, that means in a very short distance this way, I'm changing elevation drastically. And so that's going to be a cliff. Where they're far apart from each other, that's more a gentle hill. And where I've got a circle like that, that's the peak right there. And so here would be another very steep cliff as well as there. See if your neighbor has ever used a topographical map.
So actually, sometimes circle on the map, actually, I mean,
Okay. Thought for the day, one of my favorite quotes: be kind whenever possible. It is always possible. from the Dalai Lama. So let's remember that as we go through our day. Would someone be willing to give us a prayer this morning to get us started? Thank you.
Dear God, Heavenly Father, we're grateful for this wonderful day that we have to come to physics and learn a little bit more about electrons and potential energy. And Father, help us that we can prepare for this exam and that we can feel thy spirit as we study. And we say these things in the name of thy Son, Jesus Christ. Amen.
Amen. Okay. Let me just quickly remind you what voltage difference is, because I don't want you to be thinking of equations. I don't want you to understand voltage as an equation. I want you to have a gut feeling for what it means. It means if I were to reach into my pocket and if I were to pull out 1 coulomb, regardless of how dangerous that would be, and if I were to move that from rest to rest, from A to B, that vert that I would have to do, that's the voltage. That's the voltage, okay? Now, at the same time, if I'm pushing against the electric field, I'm cocking an electric spring. And if I go from rest to rest, if I look at that grand high energy equation, typically we don't worry about the gravitational potential energy because we're dealing with protons and electrons. And if I go from rest to rest, I don't have any change in kinetic energy. And so you see that the vert that I'm doing as an external agent is the change in the electric potential energy, okay? Cocking the spring. And if I have a test charge in my hand that's one coulomb, then the energy that I've stored is the voltage, okay? And that's how you should think about this idea. Now, we also have this idea of letting things go, dropping the boulder off the top of the cliff, and turning that stored energy into kinetic energy. And because there's no work done in those processes, we just release the proton, release the electron, drop the boulder. In all of those cases, the work done is 0. And so then, if I write this equation again, if this is 0 in those situations, then whatever this is, this has to be the same, but negative. If this is +6, that's got to be -6. And so I can write the change in kinetic energy from initial to final is going to be equal to the change in electric potential energy, initial to final, with a minus sign in front. And then I can even go further and say, well, that's the test charge times the change in voltage, initial to final, again with that minus sign in front. And that's where you start all of your voltage problems. Now, these are slides you've seen before. This may be the 3rd time you've seen it. And I bring them back to your attention because they are so critical. We're playing the same game between voltage and electric potential energy that we played with the electric field and force. With force, it is the electric field. If the test charge being pushed is 1, okay? Likewise, the electric potential energy change is the change in voltage. If the test charge we're moving is 1. So if you set the test charge equal to 1 in those equations, then it looks like that. Okay, and that's how you understand these things, both the electric field and voltage is it's a rate. You know, how much does 1 gallon of gas cost? and then you multiply it by how many gallons you want to buy. And I know some of you are tired of hearing me say that, but I've spoken to a lot of you who are still struggling with this idea of electric field versus electric force, voltage versus electric potential energy. If that's you, you need to fix that before you go take that exam. Okay? Now, here is the problem that many of you found challenging. It's the quintessential voltage problem. This is the one that you knew in the pre-existence, okay? This is the problem. A proton has a velocity of 1 × 10⁵ meters per second at point A, and a velocity of 3 × 10⁵ meters per second at point B. The proton's speeding up, okay? Now, it's a proton. Protons are positive. Is it moving in the direction of the electric field or opposite the direction of the electric field? If it's speeding up. Yeah, the direction of the electric field. Do electric fields go from high voltage to low voltage or low voltage to high voltage? High to low, just like gravitational goes from high elevation to low. So, are we expected to get a final answer for voltage at B that's bigger than 1,000 volts or smaller than 1,000 volts? Smaller. We want something smaller. So what we expect is a change in voltage that's negative. Okay, a change when something's draining, a change is negative. And so we're looking for a negative answer here. Now, again, we start with the grand high energy equation. We're not touching that proton. It's just racing along. And so there's no external there by the external agent. And that means whatever I have for a change in kinetic energy has to come from somewhere. It has to come from that other bucket. I've got the one filling while the other one drains. That's the picture I want you to see when you close your eyes at night, okay? So there's the starting place for most of these problems, right there. And then it's just algebra. Watch, okay? A change is always final minus initial. It started out at A, it ended up at B, so this is final, that's initial. Now, we never really care about the value of the voltage at any given point. Really, we care about the change in voltage. So we're going to leave this in this form here. Now, I plug in what I know. I know the mass of a proton. I know the speed at B was 3 × 10⁵ meters per second. I know the speed at A was 1 × 10⁵ meters per second. I know that the charge of a proton is the elementary charge, 1.6 × 10⁻⁹. I know everything in this equation except delta V. Now, folks, a word. I didn't make up the English language. I'm not that old, okay? It's not my fault that velocity and voltage both start with V, okay? That is not my fault. What I'm going to try to do when I'm doing these problems at the board is I'm going to try to write voltage with a V that's very capital and blocky as I can make it. And I'm going to write these velocity V's just as frilly and French looking as I can, okay? Yeah, those are going to be fancy. Fair enough? Now, I hope we can all agree that that's not physics. That's algebra, okay? They teach that somewhere else, not in this building, okay? Over in the Talmadge building. But if I use my algebra skills and these values for the mass and the charge, I get an answer of a change in the voltage from A to B of negative, that's a key, negative 417 volts. So if I'm told the voltage at A is 1,000 volts, well, I've got to add a change of negative 417. If I subtract 417 from 1,000, I get 583. Now, when you work the problem, you're going to get a different starting voltage, but you can handle that, right? Okay, see if your neighbor followed what we just did and could do that on the exam. Because I have a feeling, I have a strong feeling you'll have to.
You're good at like.
What's that?
Yeah.
This was 3 times 10 to the 5th, and this was 1 to 10 to the 5th. That's given in the problem.
I did it like maybe 3 times. Every time.
Just a second, folks. Got a hand up on the field. Yes, the mass of the proton, the mass of the electron, and the elementary charge are all on the exam. If you look at the sample exams, you've got the same constants
Yeah.
on your exam. All the same material. Other questions on this? Okay. Now, if we go back to those plates that are positive and negative with the uniform electric field between them, and we ask if any of these points, A, B, C, or D, are at the same voltage as the X. Are any of these locations at the same voltage as the X? In other words, if I were to go from the X to one of these points, could I do it without doing any work as an external agent? Talk to your neighbor.
Yeah. I think so too. I also.
Okay, remember, voltage difference is how much Verk I would have to do to take +1 coulomb from one location to another. Now, if I wanted to take that 1 coulomb from the X to A, I would have to do positive Verk. If I wanted to take it from the X to C, I would have to do negative Verk. But if I wanted to take it from the X to D, I would have to push this way against the electric force, but I would be moving it that way. Now, if I look at my definition of Verk, and remember it's way different than what you did on the farm, whenever I am pushing perpendicular to the motion, that's 0 Verk by definition. And so whether I take it up to point D or whether I take it down to point B, it would cost me absolutely no Verk. And indeed, any point along that line would cost me no Verk. Now, if you put on your 3-dimensional glasses, what we see here is flat is really infinite, okay? These plates come out towards you. And this line really represents a whole surface. Can you see that in your mind? And any point on that surface would be at the same voltage, meaning I could bring this 1 coulomb from the X to any point on that surface without doing any Verk. Now, we call that an equipotential surface. Again, that's not the language I would use. I would use equivoltage or equal voltage surface, but this was named long before I was born. So if I were to just randomly tell you that the voltage on that surface, everywhere on that surface, was 100 volts, and that on this surface it was 50 volts, Could you tell me what it was on that surface there? Tell your neighbor real quick. What would the voltage be there?
On the next line. Yeah. We open high low too, and we're gonna go, we're going high low. I could make 25 minutes of I'm like thinking side. So, yeah, it's. I think it's maybe about 550. You get 100, yeah.
Okay. You remember last week we learned the ET equation. If the E field is the same strength everywhere between those plates, and it is, then if there's the same distance between this surface and this surface as I have between here and here, you know, if that's 2 meters and that's 2 meters, well, then I have to have the same change in voltage. And so I would go from 50 down to 0 volts. So that brings up a really good question. If I were to put a test charge right there, would it feel a force, an electric force? Yes or no? Shout it out. Oh, a mighty shout went up in the land. Excuse me, I have to take this. Yes, honey? Sorry. You there? I'm sorry. My wife's at the vet. I think we're putting our golden retriever down, so it's not a good day. Okay, the answer is yes. There's exactly the same force there as there would be at the X or at C or any other point in between those plates. And so where I choose my 0 voltage is arbitrary. Remember, I told you you could think of voltage as elevation, and where we choose our 0 of elevation is always arbitrary. We can choose it at sea level, we can choose it at Main Street, Provo. We get the same answers either way. So where is the electric field greater, at A or B? And I just needed some way to measure attendance, so we're going to use our clickers here. If ever there was a chance to go to Disney World, this was it. This was it. That's just. This is one of those celebrity Jeopardy questions. Yes, sir.
I have a question for you. What are the numbers you're talking about?
Oh, those are volts. Or in Germany, volts. Volts. Yeah, I did. Yeah. Those are volts. Ah. I have to make 3 mistakes before they get their tuition back. That's just one. What's that?
Yeah, that's kind of.
Oh, they don't get it. Okay. You get your tuition back. Okay, have we all voted? Let's see how we did. Oh, we're not going to Disney World. The answer is B, of course. Again, just like in a topographical map, where these lines of equal voltage are close together, that's where we are changing our voltage drastically over a small distance. And you remember, we could express the electric field in volts for each meter. Okay, if I go back to this equation here, if I get a big voltage change for a small distance, that's going to give me a very large electric field. And so I would have a bigger field at B. And what direction does the electric field point at B, assuming that those are volts up there, volts? Yeah, it's always going, every single time going from high to low. Never an exception. Never. Okay? Now, suppose our electric field lines are wavy, you know, and that's what makes them different than vectors. If I were to draw an equipotential surface or line that passes through that X, which point, A, B, or C, would it pass through? Let's do our clickers one more time. Okay, last call. Good. The answer is B. Okay, yes, sir.
Can I ask you a question about the last slide, actually?
Uh-huh.
I guess where I'm confused with this, so you said the electric field changes, I might just be understanding this wrong, so is this not a plate? We're not looking at this as a plate that's giving off this change in voltage.
No, this is definitely not a plate
Right,
because the electric field is not uniform.
right, so what would this be? I guess, what is this representing then?
Well, this would be representing the field due to a more concentrated charge far enough away that the circle is starting to look pretty flat.
I see,
Yeah.
so more of a point charge.
Yeah.
Idea. Okay, thank you.
So the general rule here is that, again, to do zero vert as an external agent, I got to be pushing perpendicular. I have to be pushing perpendicular to the path that I'm moving the charge. And that's going to be true on any surface that's perpendicular to the field lines. Because that's what I'm fighting against is the electric field, the force created by the electric field. And so I have to draw that equipotential line perpendicular to all of the field lines. That would be 90 degrees, that would be 90 degrees, that would be 90 degrees. And that's the way we draw them. That's the general rule. Now, what I show here is the electric field lines, those are the red ones. And the equipotential lines, those are the blue ones for a dipole. And we've seen a dipole before in our homework. That's just a positive charge and a negative charge, the same size or magnitude charge. Now, if you go back to that topographical map, what you should be seeing here is a plateau and a sinkhole next to each other. Tell your neighbor where the plateau is and where the sinkhole is.
You know, that's like a negative equal positive, like, I've been studying how it's progressive, I've been seeing.
Okay,
That would probably be what's.
I hope everyone recognizes that the voltage is going to be higher near this positive charge and lowest near that negative charge. This is the plateau, this is the sinkhole, and this would be the cliff between them. And you would see that the electric field would be strongest in here, where the equipotential lines are close together, okay? Some years ago, my wife and I were up on Gooseberry Mesa down in southern Utah near the border, and we were collecting, with our dogs, we were collecting petrified wood up there. You can harvest it legally. Anyway, we're up there in the middle of nowhere, way up on top, And suddenly this great big group of mountain bikers came racing past, and they all just screeched to a halt and just said, Dr. Francis, what are you doing up here? I've had over 32,000 students, and I can't go anywhere without people recognizing me. That's not a good thing. Not when you're at a restaurant. Okay, so let's move on here. So if I have a spherically symmetric charge, like a point charge here, I would have these equipotential surfaces would be nested spheres, like one of those Russian dolls, okay? And the electric field lines would be perpendicular to those surfaces, so they would come out radially, and they would go from high voltage. This is from someone else's book. I apologize. I would have written high voltage to low voltage, okay? Now, in summary, equipotential surfaces or equal voltage surfaces are such that no varich is required to move a charge perpendicular to the field lines, and there's no change in voltage along any surface perpendicular to the field lines. And so we call those surfaces equipotential or same potential or same voltage surfaces. Questions so far? Going to get more interesting. Okay. The direction of field lines is always from the high voltage to the low voltage. Always. Okay. It turns out that voltage is something we call a state variable, meaning that it's independent of path. If I want to know the change in voltage from A to B, it doesn't matter whether I go straight across from A to B or whether I take some other path. And I think if we really, really can visualize what I mean by change in voltage, it's obvious, okay? If voltage is how much varich I have to do to push this thing from A to B, then what if I go there? How much varich do I have to do to go up there? Nothing, okay? And now I have to do some positive varich, but now I do zero varich, and now I do some more positive varich, and now I do zero varich, and I think we can all agree that whatever varich I did here and here is going to be exactly the same as the varich I did there. Now, again, that shouldn't surprise you because, again, voltage is very similar to elevation. And if you go uphill to school, you have to come downhill home. You can't go uphill both ways. And that means that Bill Cosby's dad was lying, okay? Because he said he went to school and back uphill both ways in the snow. Yes, sir. If I push as an external agent in the same direction it's going, displacing, that's positive varich. Now, if I've got a plus, remember, I'm always reaching in and grabbing the 1 coulomb, the plus 1 coulomb. Does it want to be next to that positive plate over there? No. So I'm going to have to push it to get it there. Now, if I went from B to A, I'd still have to push it this way to keep it from flying. But now I'm pushing opposite the displacement. So that would be negative varich. Okay. Now, we later learned that it wasn't just Bill Cosby's dad that was lying, but Bill Cosby himself. I took that hard. My brothers and I, that's how my parents got us to sleep at night. We put on that great big LP record of Bill Cosby telling funny stories, and he was our nanny. He was our nanny. I feel violated. Okay. So let's talk about lightning rods. Why do we sharpen lightning rods. You remember, a while back, I told you that in this Van de Graaff generator, there was a metal comb at the bottom and one at the top, and that it had very sharp points on those combs, and that we got very strong electric fields near a sharp metal point. And I'd like to see if I can justify that right now. We know that the electric field inside a conductor, if we're willing to wait a very small amount of time, is 0. And so that means it costs me no Verk to bring a test charge anywhere inside or on the surface of that metal. And so that means the whole conductor is an equipotential or equal voltage volume. Okay, now it costs no Verk to move the unit charge in or on the conductor. Now, if that conductor is all the same voltage, what does that mean? Well, it means that if I take my +1 Coulomb and I start at some point that I define to be voltage 0, I arbitrarily define that to be my 0 of voltage. If I wanted to bring this 1 Coulomb to that metal object, I would have to do the same amount of Verk. I would have the same change in voltage, regardless of the path. If that metal had a voltage of 50 volts relative to this point here, I would have to do 50 joules of Verk for each 1 Coulomb that I would bring from here to there. Not only that, there's several different paths I could take. I know the field lines have to be perpendicular to the surface of the conductor. We found that when we were talking about electromagnetic shielding. And so that means the field lines are going to look something like that. So let's talk about 2 different paths, okay? One path is, and this is not easy for me, not at all. I'm going to go down here, all the way down here, and then I'm going to bring it up there where the field lines are pretty parallel, okay? And the fact that those field lines are pretty parallel means that I'm going to have to Verk, 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 there. Now, the other path I could take from my 0 would be to come in this way. And you notice over here, the field lines are far apart. Oh, that's easy, that's easy, that's easy, that's easy, that's easy. Oh, that's hard, okay? Now, I think of this path as the higher educational system in the United States. Okay, you've got homework, you've got papers, you've got midterms, you've got everything all the way. I think of this path as the higher educational system in Great Britain, where you got no homework, no papers, nothing. You're just at the pub every day. And then you've got final exams that are brutal. Okay, the last week of class, everything. Now you got to do the same amount of Verk either way. And so what that means is that I must be fighting a very, very strong electric field here, much, much stronger than here. Does that make sense? See if your neighbor bought that.
So it's hard, like the field line across the field, so if you get close to the blade, it's harder and harder to there. Sometimes it's got to shit.
Okay.
Then how do you lost field up?
Now you remember, electric field is caused by charge. And so that means that if I have, okay, I already went through that. If the E field has to be stronger near that point to get the same Verk with this path as with that path, that means my charge must be concentrated near the point to give me the very strong electric field there. Now, I can demonstrate that with this Van de Graaff. And I also have a pinwheel. Now, would you verify that those are sharp points? Ow, ow, ow. Yes, sharp points. And what we're gonna do is we're gonna use the Van de Graaff to bring a whole bunch of electrons up here. And then we're gonna move those electrons down here, where they are going to concentrate at the sharp points. And when I get a high concentration, high enough to give me an electric field big enough to essentially rip those electrons off of the pinwheel, by Newton's third law, if they're being thrown this way, the pinwheel is going to be pushed the other way. So let's see if that works out. If everything goes as planned. Physics works, and that's what makes it very, very different from biology. Oh, I don't want to. Okay. Now, Clark, you said that I could just put this right on top, right? Let's see how that works. It's like a propeller hat. So you could wear this on your head and scuff your feet across the carpet and, okay. Okay, now, what does that have to do with lightning rods? So here I have a video that was produced at University of Washington. It's part of a collection of demonstration videos that they made while I was a postdoc there in an office just down the hall while they were doing this. And this device that they have here, a Tobler-Holtz machine, is just a great big electrostatic generator. It's very similar to a Wimshurst machine that I brought in last day. Now, this thing was gorgeous. It had a tiger oak case with a leaded glass front, and etched into the front was the symbol, the staff with the serpents, the symbol of dentistry. This thing came out of a dental office around 1900. And while we do this demonstration, I want you to be thinking about what possible use could they be having for this in a dental office. Okay, let's.
We'll use this model house and a high voltage electrostatic generator to demonstrate how a lightning rod works. One side of the generator is connected to a metal ball inside the chimney. This sharp rod is also electrically connected to the same side of the generator. The other end of the generator is hooked to this copper sphere, which simulates a charged cloud in the atmosphere. When the generator is cranked with the lightning rod down, large bolts strike the chimney.
Now listen carefully.
When the lightning rod is raised, the bolts stop.
You should hear hissing.
When the lightning rod is lowered, the large bolts resume.
Okay. So just like electrons were being thrown off of these sharp points here, that's the purpose of that lightning rod. It's not to attract lightning, it's to repel lightning. You don't put up a lightning rod so it'll hit your house. You put up a lightning rod so it will hit your neighbor's house, okay? When this charge separation builds up, if it gets great enough, there's going to be the lightning strike. So the purpose of that sharp lightning rod is to throw charge up around your house to neutralize that path and make the path go there. Okay? And it's also, that lightning rod is also connected by a very heavy cable down to ground, so that if you can't get rid of the charge fast enough, and if it actually does strike your house, that charge will be channeled down that heavy cable instead of through your kitchen. Questions on that? Okay. Now, I've got some pictures of lightning. Okay, you may have been there. So this one is from Iceland, and there's so much wind action going on up there that we've got charge separation within the eruption itself, and you can see that some of those lightning strikes go from cloud to cloud instead of from cloud down. Now, many years ago, when I was writing the first textbook for conceptual physics, we wanted to put a little sidebar in there about lightning. And we had a member of our faculty that was an expert on lightning. So I went to him and asked him about lightning, and he said, you know, one of the most interesting things is that usually the lightning strike goes from the ground up. It looks like it's going from the cloud down, but it's actually going from the ground up. And, you know, I respected him. I put that in the book. I felt embarrassed because it didn't seem true. But then later, some people went with a very, very super duper high speed camera and took this video. We're setting up the ionized path. Watch what happens when the first little branch hits the ground. That's cool, isn't it? That's cool. So the book's right. Who knew? Okay. Now, new topic, capacitance. Tell your neighbor what capacitance means. What does capacitance mean? My dear old father, bless his heart, when he was alive, started every single sacrament talk he ever gave with the same silly story. As kids, we dreaded it. But in the olden days, they used to have barrels of different candies, and there was this barrel of molasses in front of the general store there. And Johnny, whenever he went by, he would always sneak a little bit of that molasses, reach into that barrel and get some molasses. And it got lower and lower, and he had to reach deeper and deeper. And one day he just fell in as he sank to the bottom with the molasses dripping down all over him. He raised his eyes to the heaven and prayed, "Oh Lord, please let my capacity equal my opportunity." And that's how we would start a talk. I know, that's the way I felt too. But that's capacitance. That's what capacitance means. Your ability to hold something, okay? So how much can it hold? If I'm talking about the capacitance or capacity of a gas tank, say, the question becomes, how much can it hold before what? Well, with the gas tank, it's how much gas can it hold before it spills out, before it's ruining your shoes, okay? Now, how much gas can it hold until it spills? Now, with electricity, we can talk about the capacitance of a conductor. And what we mean by that is how much charge can it hold? Not gas, but charge. And the question then becomes, well, how much charge can it hold until what? Until it arcs to the walls, until it destroys the room? What are we going to use? And so arbitrarily, the choice was made to define the capacitance of some conductor as how much charge it can hold until we change the voltage by 1 volt relative to some arbitrary zero. See if your neighbor followed what just happened there.
Therefore, if I have one, therefore I'm better to have.
Okay. So as an example, suppose that I were to dump 6 coulombs of charge on that conductor right there, and we found that that changes the voltage, again, relative to some reference point, by 3 volts. Well, then what's the capacitance, the carrying capacity of that conductor? Well, we would take the 6 coulombs divided by the 3 volts, and that would give us 2 coulombs for each volt. Coulombs for each volt. Now we call that coulombs for each volt a farad, to honor again a dead physics professor. Not a bad thing to do. Okay, after Michael Faraday. So it turns out that 2 farads is a huge amount of capacitance, and you should have recognized that when you saw that we were putting 6 coulombs onto that conductor there. That seems silly. Okay, now how do we put those coulombs on there? Well, typically we don't just have 1 conductor, but we have 2 conductors. And then we use a battery. I went out and bought a Delco 1 volt battery. They're cheaper. Okay. And if I were to hook this battery to these 2 conductors, one to the positive and one to the negative terminals of the battery's job is to keep those conductors 1 volt apart, the same as the battery voltage. Okay, and we saw that in tutorial. Now, how does the battery do that? Well, it does that by stealing electrons from this conductor and routing them over to that conductor, so that this one becomes negative and this one becomes positive. The voltage difference from A to B has to be the same as the voltage of the battery. Okay. Now, that's important, because for every electron I steal, I leave a naked proton behind. And that means I'm always going to have exactly the same magnitude of charge on these 2 conductors. Now that means that if I'm storing 6 coulombs in this capacitor, what it really means is I'm storing a positive 6 coulombs on this conductor and a negative 6 coulombs on that conductor. And that means the capacitor itself is neutral. We're just doing a charge separation and storing electric potential energy that way. Okay, so we can have very large charges stored in a capacitor, but we always have to remember that we're talking about just the charge on the positive conductor, and that the total charge inside the device is zero. Now, the definition, remember, for capacitance is how much charge we need for 1 volt change in voltage. Now, folks, this is a general rule. Whenever you have a definition that is a ratio, something divided by something else, always put the basement equal to 1. And that will give you a gut level understanding of what it means, okay? How much charge I have to put in this device before I change the voltage by 1 unit. 1 volt, 1 volt, okay? Now, the Wimhurst machine in the basement is having some problems. Clark and I spent some time yesterday trying to get that thing to spark, and it's just, it's had better days. Yeah, so what we're gonna do is show a little video of the Wimhurst machine up in Montana. And we're gonna hook this Wimhurst machine up to a bank of Leyden jars. Now, Leyden jars are just old-fashioned capacitors that store charge. And I'll let Francis explain this. I have here a Wimhurst machine connected to a bank of what are called Leyden jars. Now, Leyden jars are just primitive capacitors, the type that Ben Franklin used. Now, Ben used an old canning jar, a glass jar, and he put a metal foil on the inside and a metal foil on the outside. The glass jar was just to keep the two electrically separated so that the charge couldn't short right from one to the other. Now, what I have here is a set of 4 Leyden jars. In the inside, I have aluminum foil, and all of that foil is connected to this structure here, electrically. On the outside, I have aluminum foil, and all of that is connected at the bottom to aluminum foil, and that aluminum foil comes right up here to there. Now, the Wimhurst machine you've seen before, it separates charge. It puts negative charge over here, leaving positive charge there when I turn the wheel. We talked about the fact that it takes 30,000 volts to throw a spark through 1 centimeter of dry air. So what I'm doing is I'm storing enough charge to build up the voltage of this thing to 30,000 volts. Now, if I connect these bars electrically to the inside and the outside capacitor bank of that Leyden jar bank. And I'm gonna move that over there. And I'm gonna leave these leads here about 1 centimeter apart again. What I've just done is I've increased the capacitance, the storage ability of this device. I've got a lot more room to store charge. Before what? Before it raises 1 volt. I still have to raise it 30,000 volts to get it to arc across. So tell your neighbor what's going to happen as I turn this crank. I have to store a whole lot more charge before I get up to 30,000 volts. It's gonna take forever for me to get up to 30,000 volts. But once I get to 30,000 volts, once I throw that spark, it's all going, okay? All the charge that I've been storing up. Yeah, that's what I mean. That's what I'm talking about, okay? So I get a much bigger spark. Now, that video did not do justice to how loud that spark was. There was some circuitry that protected us from the very high, loud volume. So let's talk about the most common type of capacitor. We call this the parallel plate capacitor, where our conductors are just plates, like we've been dealing with in the last week. And what we do is we move charge from one plate to the other, again with a battery, and that sets up an electric field between the plates, from the positive plate to the negative plate. Now, we know that that electric field strength between those plates, we've been here before, that's just the charge density, sigma, divided by that permittivity of free space epsilon naught. If I move an amount of charge that is a total charge that is sigma times A, then the voltage difference from A to B is just going to be that electric field times that distance, okay? And I can write that this way. There's the electric field, sigma over epsilon naught, times the distance. Now, the capacitance of this is just the total charge, well, that's sigma times A, divided by the change in voltage from the one plate to the other, well, that's this right here. And so if I divide this by that, you'll notice that the sigma cancels out. And what we end up with is a formula that only depends on geometry and this constant permittivity of free space. It depends on the area of the plates and the distance between the plates. Oh, and this epsilon naught's a constant. Now, if you think of capacitance as the capacity to store charge, it makes sense. The bigger the plate, the more room there is for charge to get on there without feeling uncomfortable, right? Well, what about the distance between there? Okay, it looks like the smaller the distance between those plates, the bigger the capacitance or capacity to store charge. Well, the key is before what? Before my change in voltage is 1 volt. Now, again, if my distance is very small, I have to have a very big electric field because to make this 1 volt, if I make D very small, I need a very big electric field, meaning a lot of charge, Now, what the equation says is that all I have to do is make those plates really, really close together to get a high capacitance. But the danger is if you get them too close together, you're just going to throw a spark and destroy your capacitor. And so you have to, there's a trade-off there. Now, on every capacitor, and many capacitors look like this, like a tin can, in those capacitors, you've got 2 sheets of metal separated by a non-conducting sheet, some sort of paper that's greased down. And then you roll those 2 sheets of metal up like toilet paper and then cram them in this can, okay? And on the side of the can, you have 2 pieces of information, the capacitance in farads and the breakdown voltage, the voltage at which you will destroy your device by arcing from one conductor to the other through the non-conductor. Now, if I want to know how much total charge could be stored in this capacitor here, I would just use the operational definition of capacitance, and I would multiply both sides by the delta V. And then I would look for the extreme case where I had the maximum amount of charge, and that would be at the maximum voltage difference, namely the breakdown voltage. And so in this case, I would plug in 3, remember a farad is just a coulombs for each volt. Well, every 3 coulombs I store in there, it's going to go up 1 volt. If I want it to go up 20 volts, I'm going to have to do that 20 times. So I'm going to have to store 60 coulombs. But remember, that's 60 positive coulombs on one plate, 60 negative coulombs on the other plate, so that it's neutral overall. Now, I have some capacitors here, and I definitely want the people in the front row to, you know, protect your ears. I may have told you this before, but 14 years ago, I lost my hearing due to this demo here. It was not this capacitor, but a great big capacitor bank. And I was always charging it up to 1,000 volts. Back there in 2010, I noticed that the breakdown voltage on this bank, it looked kind of like that, was 3,000 volts. So I just, more is better. I raised it up to 3,000 volts and popped that thing, and I couldn't hear anything for 24 hours. And I've been pretty deaf ever since. So I'm gonna charge this thing up.
You guys are several meters away, you're probably okay, but maybe the first 2 rows.
Okay. And now I'm going to use this little wire. Oh, I'm not gonna make the same mistake twice. The hearing aids go over here. Why are you shaking, Greg? Okay. Let's do that again. Was it loud for you? Because I can't hear anything, so. Okay, I'm ready. Okay. Now, in that example, if I use that formula, Q is just the capacitance times the change in voltage. We were raising it up to 300 volts. It's 1/100th of a farad. And that means that we were storing in there 3 coulombs, 3 positive coulombs and 3 negative coulombs. Now, I also have this modern capacitor, which has a special dielectric in it that allows us to get all the way up to 1 farad. This was not possible when I was alive, but it is now. And so if I raise this up to 5 volts, which is the breakdown voltage here, because of that large capacitance, it's storing 5 coulombs. And so I'm going to turn this on. Okay, and I'm up around 4.7 volts. Okay, and now I'm just a second. Are we ready? Oh, come on, people. It tingles. Okay, it tingles. It's 5 volts. It's only 5. It's only 5 volts. Okay, gotcha. Okay. Now, the point I'm trying to make is that a capacitor stores charge, but it also stores energy. And energy is the capacity to do damage. Energy is what you should be afraid of, okay? And when we talk about the energy stored, well, here's student 1, and we all know student 1, right? I know that electric potential energy is given by the charge multiplied by the voltage difference. So the total potential energy is just Q times the delta V. Student 1's never been right. So student 2 comes and says, oh, that formula would give the change in potential energy of a test charge moving from one plate to the other. To find the total potential energy of the capacitor, I would have to add up all the var necessary to charge it from 0. I would probably have to use calculus because the work needed to move charge between the plates would become greater and greater as the charge built up on the plates. Now, you know, as soon as student 2 said, I would probably have to use calculus, that he's not thinking right, okay? That's just not the way we want to think. So what we're going to do is we're going to use some of what student 1 said and some of what student 2 said. If I take the total charge stored, but only use the average voltage, it's going from 0 to my final breakdown voltage. The average is going to be halfway in between. And if I do that, I get this formula here. There's the charge. And there's the average voltage difference. And then if I use my operational definition of capacitance, I get this. Now, this formula tells you why I can't hear. When I increase the voltage of that capacitor bank from 1,000 to 3,000, it goes as the voltage squared. I put 10 times as much energy into that capacitor bank and then popped it with a smile on my face. Dumb, okay? So let's look at the energy stored in these two capacitors now. If I use that formula for this capacitor, what I get is 450 joules. When I do it for this capacitor, I only get 12.5 joules. There's another difference, and that is how I released that energy. Here, I released it all of a sudden through a very good conductor, a wire. Here, I put it to my tongue, a poor conductor, and slowly let it trickle out, tingling my tongue as it went. Now, the capacitor bank that ruined my hearing was storing 1,800 joules. So 4 times that energy there, and that is what did the damage. Now, folks, we have run out of time. There's a forum going on over at the Marriott Center. Have a great day.
I think it is the capacity amount, it's like, you plug in. Go ahead, Google,
How do you do it?
yeah. That makes me freak out.